Hello students, my name is Chris Allen. I am your AP Calculus AB teacher. Today I am working on this first video. We're going to look at section 1.1 and I've got a presentation here that I'm sharing with you now. So section 1.1 is a preview of calculus, so hopefully what we're going to be able to accomplish today is the following. Hopefully you'll be able to understand how calculus compares with pre-calculus. You'll be able to understand the tangent line problem in calculus and the area problem in calculus. Probably the biggest thing that you need to be aware of, and I'm not going to read all of this slide to you, is that pre-calculus and the other mathematics that you've taken before this class were more of what we would refer to as a static type of mathematics. You would find the area of a curve, area of a circle. You would find the value of a function at a point. You would calculate something that was set in the average rate of change, for example. You know that the car was here at this time, the car traveled or went to this far at this time. What was its average rate of speed? Those kinds of things. Those things are fixed, they're not changing. Calculus is the mathematics of change. So we study things in calculus like velocities and accelerations, slopes, curvature, things like this. Whereas in pre-calculus, you're looking at things that are more static. So what is calculus? So this diagram kind of gives you some idea of what you're going to be doing in this class. Now, when I say pre-calculus, I'm not just talking about the class you took last year. I'm talking about algebra, geometry, and pre-calculus. So anything before calculus. So basically what you're using is you're going to use all of the mathematics that you've learned up to this point. Then you're going to do this thing called the limit process, which then is going to yield calculus. Now, the good news, well, this limit process can be very tedious and difficult to deal with. But the good news is I'm going to try to show you the shortcuts, if you will. So here's an example of calculus versus non-calculus. So without calculus, if we were given this curve here, f of x, I would ask you to calculate f of x when x is equal to c. Now you'll notice that the point C here is clearly defined because it's a closed circle. Whereas over here, it says find the limit of the function f of x as x approaches c. Now you'll notice here that this is an open circle. This is going to be where we spend much of our time in section 1.2. So actually calculating the limit of the function. Another example. Here's a line, a linear equation. And we could calculate the slope of that line. Now, the thing is, the slope of this line is not changing. The slope of this line is constant. No matter where you pick delta x and delta y, you're going to get the same slope. However, with calculus, in particular differential calculus, you can calculate the slope of a curve. And as you'll notice that if I calculate the slope of the curve here, it's going to be different than if I calculated the slope of the curve over here. We would refer to, without calculus, the average rate of change. With calculus, we'll talk about the instantaneous rate of change. Without calculus, we would talk about what's the height of the curve. With differential calculus, we're going to actually calculate something called the maximum or extrema on a curve. Now, you did do some maximums when you were pre-calc, but this is going to be a little bit more general strategy. One of my goals is to keep these presentations pretty short, so I'm going to kind of move ahead here. I'm not going to hit every detail. Without calculus, you'd find the area of a rectangle, length times width. With calculus, you'll be able to find the area under this curved function. This is not possible. An exact area here is not possible without calculus. Without calculus, you might calculate the center of a rectangle by drawing its diagonals. With calculus, you'll be able to find the centroid of a region. Without calculus, you might find the volume of a cylinder or the surface area of a cylinder. With integral calculus, which is a different type of calculus, you'll be able to find the surface of revolution. You also could calculate the volume of this curvature. Also, without calculus, you could calculate finite sums. In other words, a countable number of things added together. With calculus, you'll be able to calculate infinite sums. Now, there are two big problems that calculus solves historically. One is the tangent line problem. And the question basically comes down to this. Here's a curve, f of x. How do I find the equation of the tangent line of that curve to point P for any location on this curve? What is that strategy? Well, this baffled mathematicians for hundreds of years. Calculus answers that question. Again, I'm not going to go through all the details, but if you look in this picture here, you'll see that there's something called a secant line. A secant line crosses the curve twice. And we know how to calculate the slope of that secant line. It's just rise over run. Now, this is very mathematical here, but here it says f of parentheses c plus delta x minus f of c. We'll get more into that later. That has to do with the limit stuff. But basically, that's telling you what's the value of the function at c plus a little bit more minus the value of the function. That's going to give us the change in y. And then this is the change in x. So that would give us what we call the slope of the secant line. Now, here's a formula. This is not a limit, but this is, again, this is the slope of the secant line. It's basically the change in y over the change in x, which is written like this. But how do we get to the tangent line slope? Well, we take this secant line, we take this point Q. Now, you've got to imagine that we're going to move Q to here, then to here, and then to, if we keep moving Q ever so closely to P, guess what happens as we get closer to P? Well, we'll see that this secant line will magically become this tangent line. The issue, though, is in order for it to become the actual tangent line, you would actually have to make an infinite number of steps to get to P. So that's why we got to use this thing called a limit, which is in chapter 1 here. The area problem. So the tangent line problem, as you saw, involves a limiting process to find the slope of the general curve. The second classic problem here, we're going to talk about the area of a plane region bounded by graphs of functions. This problem can be solved also with limiting process. So let's consider this curve f of x, and I'm trying to find the area under this curve, this pink region, if you will, from A to B. How would we do that? Well, we can see that this area kind of, well, it's straight here, and it's straight on the bottom, and it's straight on the right side. The problem is this curve up here is not straight, and it's not a circle or something that we know the formula for. This, again, baffled mathematicians for hundreds of years. What we can do, though, is think of this strategy. What if, instead of getting the exact area, what if I took 4 rectangles and I graphed the first rectangle like so that it goes right up to the left side and touches the curve, and it makes some area here that I could calculate. And then another rectangle that goes all the way up here on the left side, and I can measure, I can calculate the area of those 4 curves. And if I find these 4 areas and add them together, that would give me an approximate area under that curve. Wouldn't be exact. How could I make it better? Well, instead of doing 4 rectangles, imagine if we then did 8 rectangles. Now, which of these two do you think would probably give us a better approximation? I'm hoping you're thinking 8. Now, the good news is we could do more than 8. We could do 16. We could do 32. We could do as many as we like. And when we start learning about infinite limits and taking limits to infinity, we'll be able to get the exact area under that curve. So calculus solves the tangent line problem and the area under a curve problem. And I think that will wrap up our presentation for today. This is probably the shortest, maybe the easiest lesson in the book. The problems are not going to be very difficult, but the big idea is that calculus is the mathematics of change, dynamic, whereas pre-calculus is more static. And then the classic tangent line problem and area problems So now you'll need to watch the next video on section 1.2 and complete some of the problems in the module. Have a good day.